Assalamualaikum and good day. So today, after we finish on chapter 1, introduction uh, and the noise, then chapter 2 is on the AM, amplitude modulations, and chapter 3 is on the angle modulation. Now we go to this chapter 4, which is the pulse modulation. So by the word pulse modulations, we here by the word itself, we already know that there will be a modulations on the perform on the pulse, okay, involving the pulse signals. So this basically the digital communication system, okay, DCM, no, DCS, digital communication system. So this at your transmitter sites, and this is at your receiver sites. So this is taken from other sources. So this is from the receiver site and towards to other destinations. So you have see, this is your RCV receiver. So this one is the channel, okay, the channel that where we transmit our signals, the medium. So this is our all part of our transmitter, and this is medium, okay, transmission medium, and this is the receiver parts, okay. So we're not going to discuss this in detail because this is actually covered in one of the subjects, if I'm not mistaken. The name is digital communication system, which we are not taking for your programs, okay. So this is just good to know for you so that you appreciate the relevance of studying this chapter, okay. Introduction. In the early 90s, the telecommunication network is changing towards digital world. Okay, so it's in the early 90s with the rapid advancement in the field of VLSI, very large scale integration, and microprocessor. Several telecommunication components such as transmission lines and switching has been using digital signal in their operation. Therefore, the information signal must be changed to digital form. Okay, so it's not analog. We cannot forever analog. Okay, so that it can be transmitted through this digital network. Okay, digital network. Several techniques requiring full coding of the original signal use. So passcode modulation, differential passcode modulation, DPCM, adaptive PCM, delta modulation, and adaptive delta modulation. So we'll be covering quite detailed for this PCM and also on this delta modulation. Okay, on this three is not so much. Okay, so digital modulations are the advantage of performing the digital modulation instead of the analog modulations. The relevance, the advantage is immunity to noise. Okay, I think you know as well when we do this digital signal, right? We already quantize it. We already some level. This is 1 and this level is 0. If you have analog signal, it having too much variations of amplitude. Okay, in the digital we already sample quantize and coding to certain value only. So that's why it's if we have noise, it much less disturb because we already do this step. Okay, easy storage and processing. Okay, seems that the slide have, so I put it here. Okay, and I put it here as well. Sorry for that, please correct them in your slide. Okay, continue again. Regenerations, easy to regenerate, easy to measure, okay? Enable encryption, just like what you see in the previous slides. We are able to encrypt them if needed. Previous. So this is encrypt stage here. Okay, at the transmitter side. Of course, at the receiver side, we will have the inverse, which is the decryption. Okay. Data from several sources can be multiplexed, adding and transmitting using the same digital communication system. So error correction detection can be utilized for this detection for the digital modulation. So disadvantage is for the digital modulation, so it requires a big bandwidth. Analog signal need to be changed to digital first, okay? And not compatible to analog, of course, this is digital, and you need to have synchronizations. So in terms of the bandwidth, bigger bandwidth, let's say your analog is just 4 kilohertz. If you want to make them digital, you will learn later on. Okay, 2 times 4 kilohertz times 8 bits, you need for 64 kilobyte per second. So the bandwidth needed minimum is actually 32 kilohertz. So you can see for the analog, it only requires 4 kilohertz. However, the corresponding is actually 30 kilohertz in the digital modulation. This is one of the disadvantages. Okay. Okay. So figure 0.17 is A is the transmitted analog signal, and this is the received analog signal. I think I've shown you in the class. Is the noise that present, right? When I draw on the whiteboard. Okay, this is pretty much the analog with the noise. Then this is the digital signals, transmitted digital signal. We have, for example, this is 5 volts, and this is negative 5 volts. Okay, and if we have the noise, okay, there is noise, but it's still able, we can still distinguish. This is 1, for example, this one is 0, for example. Okay, but for the analog, because we have varying range of the y-axis here, if we have the noise, it's a bit easily disturbed and more challenging in order to the noise immunity. So we have, if the noise is too large, we cannot predict what is difficult to predict the original transmitted signal. Okay, but if we digitalize them, it's easier because it's just look like levels. Okay, levels, because it's when digital, you will learn later. We do sampling, quantize, and coding. So transmission method for analog and digital signals. Okay, so we have these analog inputs. Okay, and we have this analog output. Okay, so this is the analog signal, and this is the baseband signal, baseband. So if we have if we're going to actually just the analog signal. So for the analog input, modem, analog signal, modem, analog output. For having the digital channel system, we have digital input, encoder, digital channel, decoder, digital outputs. And then for the if we have analog channel, digital input, modem, analog channel, modem. For the digital channel, if we have analog input, analog output, so we require ADC. and encoder, and the inverse operation, decoder and DAC. This is referring to digital analog converter, and this is analog to digital converter. So this is if we have this analog inputs to have analog output with the analog channel, we have analog to digital converter and encoder, then we have a modem, and have at the receiver side we have modem and inverse operations. We have DAC and decoder. So this is DAC, yeah? Okay, in typo here. So we have here is pulse modulations, okay? So because this chapter is about pulse modulation, so we discuss on the pulses of signals. Okay, pulses modulation consists of PAM, pulse amplitude modulation. So when you see the word amplitude, means there will be changes in amplitude. So logic, right? And then we have pulse width modulation. So this is changes in the width of the pulse, okay, which is the tau, okay. And then pulse position modulation, tau d, which is pulse delay proportional with your PM. And the next is pulse chord modulation. We change to n-bit series. Okay, so don't worry, we will learn along the way. So we have this is the your information signal. Okay, and this is the pulse. Okay, we go to here, the first one. Okay, pulse amplitude modulation. If you see, where's the amplitude is increased, okay, and increase of in terms of the amplitude, regardless whether it's positive or negative, okay, we're going to have increase in the amplitude for the pulse amplitude modulation. However, just for the corresponding positive, we're going to have positive here, and it will be the negative here. But in terms of the magnitude wise, okay, it is correspondingly proportional. Okay, so this one is the highest magnitude, so that's why you have the highest magnitude. This one is the highest magnitude, okay, and then the that's why you have the highest here, but with negative lah, okay, because it's corresponding. The next is ppm. Ppm is the pulse position modulations, okay. It will have this pulse delay proportional to Vm. So if you see here, this ppm, there is difference in the positions of the pulse, okay. So we will learn later, okay. So this as what you learn in the can relate with the amplitude modulation, because we have modulation performed in terms of the amplitude of the carrier, so it is easily affected by the noise, because our information is in the amplitudes, which is the envelope, right? So similarly, analogically, so AM pulse intimidation is easily affected by the noise, okay. And compared to this ppm is less susceptible to noise compared with this PAM. And of course, the pulse width modulations is the most is the less susceptible to noise. If you see here, pulse width modulation is that the one that have you see here, the magnitude is increased. Okay, no, sorry, the width of the pulse is increased as we nearing to the maximum, and then as we going to the minimum, because this is the minimum, right? Here, even though the magnitude is, let's say this is 10 volts, 10 volt, but this one is positive 10 volt, but this one is negative 10 volt. So that's why it's going to have the narrowest, okay, the narrowest pulse width, okay. But for the maximum here, it's going to have the maximum width, pulse width. So sampling theorem, okay, sampling theorem is when an analog signal can be proper sampling, when an analog signal can be exactly reconstructed using the samples. The sample contains all the information needed to recreate the original waveform. So we must careful when we do our sampling, because we need to do a proper sampling in the sense that this sampling still able to represent the original waveform, even though we only take certain value for a certain sampling for corresponding sampling rate. We don't, if we don't care too much on this, if we don't carefully do this sampling, our samples, will not be representative of um, our original signal. So here is the analog, okay, um, the analog input. Then you will have to go to this sampling. Then you're going to have first sample signals, digital. So present by this solid line. Okay. For example, if this error signal is DC value, that's why it's only straight lines. So this is the sampling that perform. 1, 2, 3. We sample for period, for a selected time period, or okay. And we have this, for example, analog frequency, okay, the SC. So let's say we have 0.09 sampling rates. So what does it mean by 0.09 sampling rate? So if we have less 10, as you know, frequency is actually 1 over T. Okay, so this one is sampling rate is the sampling. So F 1 over sampling over 0.909 second. Then we not second, depends on the units. It can be microsecond, whatever. So the frequency is actually equals to 11. Okay, 11 FM. Okay, proper samplings. Okay, sampling rate. Okay, so this is your FS. Okay. So the sample seems to represent different sine wave. So if we have a lower, let's say we have lower sampling rate, 0.05 FM. Okay. So if you see here, we have 11 FM. Okay. We with higher sampling rate, which is 0.09. Let's say we have 0.95 sampling rate, which is 1 over so if we don't choose proper sampling rate, for example, okay, for example, this one 0.95 sampling rate, okay, sampling rate, where here the Fs is almost equivalent to your Fm, okay. So this is improper sampling in sense that you see here your sampling actually represent this kind of signal, this sampling signal, which is actually different than the original signal. So that's why it's one of the bad outcome when you don't do proper sampling. Okay. So it need to be sampled at very much smaller. Okay. So this is known as aliasing. Okay, this phenomenon where sinusoid change frequency during sampling. Okay, this is known as aliasing, where sinusoid change frequency during sampling. Okay, frequency and phase can be affected. Okay, so this is, let's not too high. Let's say we have the low numbers, which is means that it will have more sampling. Okay, so for a given signals, okay, we have fc equals to 3 fm. Okay, so 1 over 0 0.31, so you're going to have 3. Okay, so you sample 3 times in a complete period. Okay, so you're sampling 3 fm. So you have here the sampling. If we want, this is the original signal, and if we want to follow the sampling, it's still able to represent the original signal. You can see, right, the shape is almost maintained. So this is where we have the sampling, which is almost correct lah. So in D, the sampling frequency is less than the Nyquist frequency. So what we learned in the Nyquist frequency, we can refer on the module as well for more detailed reading. So for the Nyquist frequency, your frequency sampling, okay, should be at least equal, okay, at least equal here to your double of your FM. Okay, it cannot be less. So if it's less, this is what happened. You have improper sampling. So you need to have at least 2 FM double. Okay, let's say if your signal, information signal is 1 kilohertz, it should be having your frequency sampling should be actually 2 kilohertz minimum. So then the original signal can, if it's less, cannot be reconstructed. So that's why we have sampling theorem. We should follow this Nyquist or Shannon theorem. Okay. So we have 3 sampling methods. Okay, we learned about this sampling. Ideal sampling, of course, by the word ideal. This is not practical in real life. Then we have natural sampling, where we sample even the, the shape here. We just like cut them. And then flat top sampling, by the name flat top, we have this flat here. That's why it's flat top. Okay. So in every sampling method, the pulse amplitude is directly, proportional to the amplitude of the information signal, directly proportional. If you can see, right, they are here directly proportional. Practically, an ideal sampling is difficult to generate. Yes, because it's ideal, right? We don't work in ideal world. The ideal world, the real world is practical. However, by using an ideal and natural sampling, noise error can be eliminated. So this natural sampling, which is not the case for flat top. Okay, flat top, because we have, if you see the flat top, it just make the amplitude flat, from which one of the available value for this one, it take this value, then the flat. But for the natural sampling, we follow the amplitude is following the shape of your information signal. So the ideal samplings, you see here is this one is an impulse, right? Okay, so it look like impulse, impulse trend. Okay, so ideal sampling MT. This is your modulating signal, your message signal. Then mix with your digital signal ST, which is your impulse trends. Okay, to produce MST, sample message signal. Okay, so we're going to have this value varied by your amplitude variations of your original message signal. So it must follow this Nyquist or Shannon theories. Okay, theorem. Okay, Fourier series for impulse trend. So ST 1 over TS 1 plus 2 cos omega S and so on. And omega S is 2 pi over TS and 2 pi Fs. This one is logic. Then Fs should be greater or equal than 2 FM. Therefore, for the MS sample message signal is actually the mix of multiplications, okay, because it's a mix multiplication of your empty SD. So this is the result of that, okay. And you have dot here because it's we have more of them. Depends on what's question specified for you. So this is in terms of this time domains, and in terms of this frequency domain. I believe you learned in this goes back to your signal and system. The prerequisite subject for this, the subject required for you to actually enroll for this subject. So this is your information signal, which is the analog and continuous. Then you mix them with the sampling signals, sampling frequency. So you have this impulse trend, then the sample message, then you will have this corresponding, cantik lah, can pretty nice following the amplitude of the signal. So this one is of course is like a discrete, okay, like a discrete but continuous. In terms of frequency domains, okay, so this is your message signal, and the equivalent impulse trend, then you're going to have these triangles, okay. So refer to your signal and system, okay. So this first resulted in this and this into this, okay. Refer to your signal and system, okay. So I'm not going to teach it here, okay, otherwise it'll be longer, right, the video. So reconstruction, so if you see here, okay, this is M message signal, okay, in terms of frequency domain, okay. So with the pass signal of your SD, okay, in pass train, then is at the transmitter side, then you're going to have your sample message signal, which is this, and it will undergo a low pass filters, okay. So it means that we only take the low frequency signal. If you see here, there is a lot of high frequency. For example, is multiple, this is actually high frequency, okay. This is also a high frequency, okay. Then you go to a low pass filter, and you have again here, then you will end up the received message signal. You're going to have this MR omega, okay, which is actually is here, okay, the one that actually in the middle. So we take them, okay. This is the one that we're going to have at the end, okay. Depends also on the this one is not necessarily one, it depends on the if we have amplifier or whatever, whatever. So we have this TS is the amplitude, okay, of this your transfer function, okay. Okay, sampling process shown previously used an ideal pass signal, which is impulse trains, okay. However, it is quite difficult to generate an ideal pass signal practically, okay. So this is true, okay. So ideal pass, so that's why we ideal. So I think we go for this natural sampling and the practical one, okay. Not, I mean, ideal, and you have the counterpart practical, which is the natural sampling. The usual path signal generated is shown below. Okay, usual path signal. So you have ST path signal with the amplitude A and the path duration tau. Okay, path duration, this one. Not the entire duration. Entire duration is this. Okay, complete. This one is concerning the path duration only, the path where we have the values. Okay, and this is your TS. Okay, which is the path period. Okay, or it's shown here. Okay, so ST is equals to amplitude path width over TS plus 2 amplitude tau of the TS, summation of the N1 until infinity, depends. Let's say we say 3, 4, depends. And then Cn cos 2 pi nt over Ts. Okay, where Cn, the Cn component is actually sine n pi tau over Ts equals to n pi tau over Ts. So this is actually sinc function, the one that you already learned in signal. Okay, so this sinc function in brief. Okay, so you have this information signals. Okay, information signal with MT, and you have this path signal. So let's say we take pulse amplitude modulation. Okay, system modulating scheme. Okay, pulse signal modulation, pulse amplitude modulation scheme. So if we're using natural sampling, okay, so the value of the message signal is samples for every of here. For example, this one, we will sample here, okay, and then we sample here for the natural sampling. So that's why we have here, okay. For the flat top sampling, yes, we sample for every similar durations of path width. However, the amplitude will be flat. That's why it's a flat top. Okay, so it will be flat. So the path width must be much smaller than the path periods. Okay, because okay, so the path width, the width of your path should be much smaller than your path periods. Okay, this is, I think this is logic. Cannot be similar. If they're similar, then there is no path. Okay, doesn't look like path. Okay, so mathematical analysis for this MT. So you have MT message signals with the path signals. Then similar to what you have. Okay, now is to analyze it mathematically. Fourier series for path signals, okay, is ST. Okay, Fourier series. ST equals to tau over your TS over your path periods plus 2 tau over TS with N1. Okay, starting from 1. So you need to see this properly here. Okay, sometimes it's from 0, sometimes it's from 1. I mean, from the range. Okay, please see this carefully, so that you don't make mistake in the test or exam. Sinc n pi t path width over Ts cos 2 pi nt over Ts. Okay, this one you can refer back to your signal system appendix. Therefore, the sample signal MST equals to MTST. So similarly, okay, MST is equals to MT times ST. Okay. From the sampling process, okay, the sample signal MS is equals to M tau over Ts, MT times 2 tau over Ts, and Cn cos 2 pi nt. So this is actually results in the t times with your mt lah. Where Cn is equals to sink, the one that we already learned just now. Okay, so if pulse width is much less than pulse periods, as it should be, right? Therefore, the first few harmonic, first few means not n1, but first few, the first earlier harmonics, okay, sync n pi tau over ts can be approximate to 1 for the first few harmonics, okay? Therefore, if you therefore mst equals to m tau tau ts mt 2 tau over ts cos 2 pi nt over ts. So Cn is equals to 1, okay, for the first few harmonics. So this Cn, because Cn is equals to sync, okay. So this is the further simplification, okay. If in the condition that your pulse width much less than your pulse period, okay. So taking that, let's say mt, your message unit is actually cos omega mt. So let's say here you see only this, right? Means that we assume em is equals to 1 for this one. Okay. Replacing mt inside this signal that we have. Okay, you replace here and you replace here. Then you have more expanded form of the sample message. Okay, so you have this component omega m, then you have omega s plus omega m. So this is just the cos a and cos b lah. Okay, identity theorems. Then it will be continuous depending on what value of n given or specified. Okay, but naturally it is continuous. The choice of sampling for fs, okay, sampling frequency fs, must follow the sampling theorem to overcome the problem of aliasing, okay, what we see just now in the previous slide, aliasing, where the sampling do not follow the Nyquist or Shannon theorem or limits, sometimes we call limit. It doesn't properly represent our information signal in terms the sample doesn't really represent of our original signal. So for the sampling frequency for the fs which is less than 2 fm max, okay, so we're going to have overlapping. Okay, this is where the aliasing happen. Okay, but if we sampling our frequency with fs at least equals to 2 fm, okay, so we're going to have proper sample signal. A band limited signal that has a maximum frequency f max can be generated from the sample signal if it's sampled at a rate of at least 2 fm. It's not at least means at least equal to 2 fm. So you have the first sample, then the second double, and you have triple. So this is your FM. So let's say this is 100, let's say 100 kilohertz. This one be 200 kilohertz, and this one is 300 kilohertz. Okay. So this is the passport modulation. Okay, so the one of the modulation scheme for this digital modulation signals. So a method used to represent an analog signal in terms of digital world. Okay, in terms of digital world, constitute of 3 processes. Okay, for the passport modulation. So it's a sampling. We sample first. Okay, just like we have learned just now, we do the sampling, whatever, right? To sampling need to be greater than your 2 fm, which is your f max. Let's say you have variable values, then we take the fm, which is the fm max, message information max. Okay. Then quantizations of the amplitude. See here, quantize amplitude of the sample signal. So we're going to quantize of the amplitude of our sample signal, and then coding of the quantized sample signal into our digital signal. Okay, so this is actually what PCM involves. Okay, sampling, quantize, and coding in terms of block diagram. So we have analog signal. This one is what we're going to generate at your transmitter side. So you're going to have the sample pulse signal, okay, which have fs at least or greater than 2f max, 2fm max. Then you have this anti-aliasing filter, so that to remove the aliasing that we know just now, right? That's why this anti-aliasing filter. Then you have low pass filter. Then SH is a sample and host kits, and this is, you know, is the ADC, and this is the line encoder. Okay. So sampling is an analog signal must be sampled at least at the Nyquist rate to avoid sampling. This is the fs greater or equal to fm max. Then quantization and coding. Quantization is actually we're going to is actually the amplitude changer. Okay, we quantize the amplitude, and then process of estimating the sampled amplitude. You see here, not the actual amplitude, but the sample amplitude into a value suitable for coding. So this is the involved this ADC lah. A fixed number of level, including the maximum and minimum value of the analog signal. So you're going to have maximum number, for example, 5 volts, and negative 5 volt. So maximum and minimum value of this analog signal, because analog signal, of course, you're going to have a maximum and minimum, right? And you're going to quantize this according to the fixed number of levels. Okay, we'll learn more detail afterwards. Okay, number of level is determined by the number of bits used for the coding. Let's say the coding is using 3 bits. Okay, then your quantization level is 2 to the power of 3. You're going to have 8. Okay, you're going to have 8 levels. Okay, 3 terms that commonly used in the quantization process is the quantization level, L equals to 2n, which I shown just now. Quantization level depends on the number of the binary bits n used to represent each sample. For example, F3, the quantization level will be 2 to the power of 3 equals to 8 level. So in this example, first level, level 0 is represented by 0, 0, whereas bit 11, bit 111 represent the 8 level because we have 8 level. Okay. Quantization interval is the interval between the quantization level. Okay. So magnitude difference between quantization level. For example, let's say you have a sample signal that has a 5 volt amplitude. Okay. For example, if you have 5 volt amplitude, so V peak to peak means peak to peak to the next peak. Okay, which is negative 5 volts. So it is 10 volts. Okay, divide by the quantization level of 8 level. So therefore, quantized interval delta V is the V peak to peak, okay, V peak to peak over your quantization level. So you get 1.25 volts. Okay, then you have a quantization value, the value that we quantize. So we take at the value of the middle voltage. Okay, we quantize the value at the middle voltage for each quantized level. For example, let's say we have n equals to 3. Quantization would have 8 level, right? 8 level, and a sample sinusoid signal with plus and positive negative 5 volts. Okay, The middle quantization level for level 0, which is here at the minimum, okay? So taking the minimum is -5 because it's taking, because V naught, okay, for the level 0. So the minimum is -5. And logically, logic, right? So the quantized value will be higher because it's we quantize. And plus with the half, okay, half of your quantization interval. So -5 plus this value. So the you will have the for the variable 0, okay, for level 0, the quantization value will be -4.375, and don't forget the unit volts, okay. In this example, for example, that is in level 0 segment will be represented by with a 00 by bit 00 with a voltage, with a quantized voltage value of -4.375 volt. The difference between the sample, okay, you see here the difference between sample value and the quantized value result in quantization noise, okay. The difference, okay, because there is different, because we take this, for example, -5 volts here. This is the original signals, okay. Let's say we want to represent this one, it will be 4 point -4.375, okay, for the minimum. But we have the difference between this and the actual sample signal. So that is the quantization noise. For voice communication, 256 levels are commonly used. This is actually means 8 bits, okay, 256. So please refer to the module, okay, because I want to encourage you to read the module. What system actually using 16 bits? Okay, refer to your module. Next is the uniform quantizations, okay. We will go to this in the next lecture, okay. So assalamualaikum and good day. Thank you.